Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the Bitcoin Optech newsletter. And this week we will be going through newsletter number 335, published on 3rd of Jan 2025. As always, it has the news section comprising of those news articles. And we have a new addition. We have some weekly segments and some monthly segments. So we have a PR review club. There is one PR review club that is covered in the newsletter monthly. And there's also one software and client release section that is monthly. And now this year onwards, I believe they have introduced a new monthly section and they have titled it Changing Consensus. So every month, once out of the four weekly newsletters that are published every month, one newsletter will have this section called Changing Consensus, which will probably talk about, as the name suggests, changing consensus and proposals regarding more or less about soft forks. And we have the news section, we have this a new introduction, Changing Consensus, and the releases and release candidates. It's a weekly feature, and notable code and documentation changes, all right? Uh, I was going through the newsletter and I thought that the changing consensus section would interest the listeners more instead of the news articles. So I decided that we will spend this week's session in covering this section. There's a lot to talk about. One, two, three, four, five different proposals that we can discuss. And that is adequate amount of content to cover throughout the span of 1 hour. So we'll start with this. We'll just go through the preface first. This week's newsletter links to information about long-standing de-anonymization vulnerabilities in software using centralized coin join protocols and summarizes an update to a draft BIP about chill DKG distributed key generation protocol compatible with triplet threshold signing. And we have talked about both of these topics in our preceding sessions. We talked in one of the sessions, I believe, almost 2 or 3 months ago, or at least a couple of months ago, we talked about chill DKG. And we have also talked about this de anonymization attack. I believe it was probably 3 or 4 weeks ago. So that has been covered in the news section. Again, maybe some more vulnerabilities or some breakthroughs in what was mentioned in the preceding sessions. Also included are our regular sections summarizing discussion about changing Bitcoin's consensus rules, announcing new releases and release candidates, and describing notable changes to popular Bitcoin infrastructure software. We will jump directly to the changing consensus section. I believe everybody knows what consensus rules are. They are rules that every participant on the Bitcoin network has to adhere to, whether you are a miner, whether you are a node runner, or whether you are just a user, you will have to adhere to these consensus rules, which cannot be circumvented or bypassed by anyone on the network, right? So there are a set of rules which are known as policies, right? And policies vary from a person to person, vary from a client to client, and you can have your own custom policies. And having custom policies, it does not eject you out of the system. If you are adhering to a policy that majority of the participants in the network do not adhere to, you will still continue to be a part of the network, right? Even though maybe your connection with the rest of the peers might hinder the transaction that you broadcast or the information that you gossip among your peers on the network might not be relayed as quickly, but eventually you are still a part of the network. However, as far as the consensus rules are concerned, then these are non-negotiable. If you are not abiding by the consensus rules, you are ejected out of the network and you are not a part of the Bitcoin network anymore, right? So if you are running a Bitcoin client, for instance, and you are not sticking to default policies, you are making changes to your policies, you have your custom node policies or custom mempool policies, you will still exist and continue to be a part of the Bitcoin network. But if you, for instance, make changes to the code base of an existing Bitcoin client and don't comply with any of the consensus rules, you'll be ejected out of the network. So that's basically what consensus are. They are more stricter. In fact, they are non-negotiable. They are a set of rules which are non-negotiable for you to participate and interact with the Bitcoin network. A new monthly section summarizing proposals and discussion about changing Bitcoin's consensus rules. The first one is CTV enhancement opcodes. Developer Moon Settler posted to both Bitcoin Dev and Delving Bitcoin to propose two additional opcodes to be used in conjunction with the already proposed Optech template verify. These are the two opcodes. Okay. Just a reminder, if anybody has anything to say, please feel free to unmute yourself and talk. Once in a while, I will have a look at the chat section to see if somebody's posted something. But other than that, if you'd like to speak, please feel free to unmute yourself and speak without seeking permission or waiting for me to stop. So the first opcode that has been proposed is op template hash. It takes a list of transaction elements and converts it into a CTV compatible hash. This allows stack operations to specify details about the inputs to be used, the number of inputs, the lock time, the value of each output, the script of each output, the number of outputs, and the transaction version to use. Op input amounts puts the Satoshi value of some or all of the inputs on the stack, which can be used as a parameter for op template hash. Example to require an equal output value. Together, these opcodes can create vaults with similar properties to those possible with BIP355's opvault. The opcodes may also be convenient for implementing more on-chain efficient types of accountable computing. In addition to other contract protocols, discussion on the Delving Bitcoin thread was ongoing at the time of writing. So this specific article or proposal deals with covenants. Okay, we'll try and briefly go through what covenants are, what vaults are, what OpCTV is, and what these two new opcodes are. Obviously, without digging too much into the details of what the proposal is due to time constraints, but we'll try and do justice to it. Firstly, what covenants are. Okay, what are covenants? Linguistically, covenant is a promise, right? Linguistically, in English language, a covenant is a promise that you make to someone. Okay, now in Bitcoin's terminology, what do covenants refer to? It is basically a commitment, like I said, a promise or a commitment. So it is a commitment that you make, and that commitment is a set of conditions, is a set of predefined conditions that you commit to, and the commitment is such that you will adhere to it while spending that transaction. Okay, so up till now we are all familiar with how we lock the inputs of a transaction, right? In Bitcoin, like whenever you want to spend a transaction, you need to have access to the private key, right? What does the private key do? The private key unlocks the inputs. The private key unlocks the inputs. So if you want to create a transaction, your the input of your current transaction is the output of the transaction from which you are spending, right? So we lock the inputs of the transaction. So if Alice wants to send one Bitcoin to Bob, Alice can decide to whom that one input will go, right? Alice can decide whether she wants to send it to Bob or she wants to send it to Charlie or she wants to send it to Dan, right? But once that Bitcoin goes to Bob or Charlie or Dan, Alice has no control over that transaction, right? Then it's absolutely Bob's prerogative or Charlie's prerogative or Dan's prerogative. It is they who decide how they want to spend it further, right? So Alice can only lock the input. Alice can decide that a UTXO in her position can be sent to a certain person, or under certain set of conditions it can be spent. But once Alice loses ownership of that transaction and of that UTXO, and that UTXO, its ownership is now transferred to somebody else, then Alice has no intervention in that, right? Because that UTXO now has a new owner, and that new owner will decide how and to whom and under what conditions they want to spend that UTXO. What covenants do is that covenants give you the provision to lock the outputs of a transaction, right? So up till now, we are familiar with the concept of locking the inputs of the transactions. Covenants give you a provision to lock the outputs of the transaction. Okay, so let's assume there's Alice and there's Bob and there's Charlie. Okay, now in the conventional manner of spending Bitcoin, Alice can decide that Alice wants to send one Bitcoin to Bob, right? But once that Bitcoin is owned by Bob, once Alice sends it to Bob and Bob owns it, then Alice cannot decide to whom that output Bob will spend to, right? But what covenants do is that they allow you to lock the outputs. They allow you to lock the outputs. So even before Alice sends that Bitcoin to Bob, Alice can lock that Bitcoin in such a manner that once it reaches Bob, Bob can only give it to Charlie and to nobody else, right? That is the concept of covenants, locking the outputs of a transaction. Okay, committing to a template, committing to a template such that the transaction can only be spent if you adhere to that commitment. Okay. Now, one catch here is, I mean, prima facie, you might feel that this is not fair, right? Because once Alice is sending that Bitcoin to Bob, it's Bob's Bitcoin. Alice has no business deciding to whom does Bob further forward that Bitcoin, right? But the catch here is that it is Bob who decides. It is Bob who decides. Okay. Bob decides to whom he wants to send that Bitcoin or in what conditions he wants to send that Bitcoin and gives that template to Alice and gives that template to Alice. All right. We are familiar with what P2PK etc. Is, right? It's referred to as a legacy transaction. What's P2PKH? We have a public key, we hash it, right? We hash it and we create an address. We have a public key, we hash it, we create an address. There's more to it, obviously. We append something to it and we prepend something to it and we convert it into base 58 or base 32 or base 32M, etc., right? But the gist is that you have a public key, you hash that public key and you turn it into your address, right? And when you want to receive payments, you receive payments to the hash of that public key. That's P2PKH, right? We know what's P2SH, right? We create a script, we hash that script, we convert that the hash of that script into an address, okay? And then as recipients, we give it to whoever we owes us Bitcoin, right? And then they pay it to that script. So that's P2SH, right? Like that, we create a template like that. Bob will create a template. In that template, Bob will specify certain conditions. Bob will commit to certain conditions. Okay, what could that those conditions be? They could be inputs that will be used. They could be the number of inputs. They could be the lock time. They could be the value of each output. They could be the script of each output. They could be the number of outputs. They could be the transaction version. They could be the address of the recipient, right? They could be all of these. Or they could be a subset of these, right? So the just like you hash your public key and convert it into an address and somebody pays to that address, it's P2PKH. Just like you hash a script and you convert it into an address and somebody who pays to that address, it's a P2SS transaction. You create a template, right? You create a template in which you can specify some of the conditions to which you lock the outputs of the transaction and you hash it. And then you give that hash, okay? Then you give the hash of that template to whoever owes Bitcoin to you, and then they pay to your template. Then they pay to your template, okay? And when you want to spend it, you will only be able to spend it in accordance with the commitments that you have made, okay? So if I create a template and I say that my transaction will be locked for 30 blocks, and my transaction will let's say we have version 3, okay, my transaction will be locked for 30 blocks and my transaction will be of version 3. So I create a template, I hash it, and then if somebody owes Bitcoin to me, I give that template to them and they pay to that template, okay, which ensures that after I gain ownership of the UTX, so if I want to further spend it, I will only be able to spend it with the transaction version that I have specified in my template. Let's say 3 in our example, and I will only be able to spend it if I have if 30 blocks have been passed. If 30 blocks have been passed, okay, uh, as I have specified in my template. So that's the concept of covenants. Broadly, what do covenants do? Covenants uh, lock the outputs of a transaction. Okay, so the spender commits to a certain set of predefined conditions. The spender commits, okay, because covenant is a promise or it's a commitment. So the spender promises or commits that they will only spend this transaction in accordance with the set of conditions that they have defined, right? And covenants can be achieved in multiple ways. You'll find a lot of proposals. OpCTV plus OpCSFS is one of them. Opcat is one of them. There are others as well, right? Okay, there are others that add more to it. There's an enhanced proposal that contains a subset of multiple proposals. So there are multiple opcodes that can enable covenants. The one in discussion here is OpCTV. As the name suggests, Optech Op check template verify. You create a template. In that template, you specify the conditions based on which you intend to spend the outputs of the transaction that you receive. Okay, and then you hash that template. Okay, you hash that template, and when you wanna spend that transaction, you should fulfill all of these conditions. Only then will you be able to spend that transaction. Okay. Now this can have multiple use cases. One use case, like in a very surface level use case, if I had to define, is that let's say Alice owes 1 Bitcoin to me. Okay, Alice has to pay 1 Bitcoin to me. So I create a template. In that template, I enter the recipient's address as my address. Okay, my another address. one of my addresses, okay? And then I create a template and I give it to Alice. Now Alice gives that one Bitcoin to me. Now, because that Bitcoin has committed to a template, that Bitcoin can only be spent to the address that I have specified in my template. And I've specified my own address. So even if somebody hacks into my private key, they can only send that transaction to my own address, right? Because I have locked the outputs already. I have committed to the outputs. I have created a template in which I have specified the recipient's address, and the recipient's address is my own address. So even if somebody hacks into my wallet and gets access to my private keys, they can only spend that transaction to the address which is already specified in the template, which is my own address, right? This is a very surface level use case of it. And that is why when you hear about covenants, you often hear about vaults. I am assuming most people here should know what vaults are. If this description is not very long, we can maybe go through it. Vaults are a type of covenant that require two separate transactions to appear in two different blocks in order for a user to spend money from their wallet. The first transaction signals that someone is attempting to spend the money and gives the user a chance to block the second transaction that completes the spend. What's a vault basically? Vaults are usually used, it's not necessary, but vaults are usually used for a large volume payments, like huge payments where a slight mistake could lead to the loss of life-changing funds. Okay, like for instance, if an exchange is transferring some huge amount of money, in that situation, people would want to use vaults. So what are vaults? If you have if you want to make a payment, right, you usually conventional way of making payment is how the sender directly sends it to the recipient, right? If Alice wants to send one Bitcoin to Bob, she'll directly ask Bob for her address and she'll send it to Bob, right? But there are possibilities that Alice might make some mistake while she is sending that payment. Maybe she copies the wrong address or something like that, right? So if the amount is small, maybe the margin for error is bigger. But if it's a huge amount, then you don't want to take any chances, right? So what vaults do is that you send uh, a UTXO from the sender to the recipient in two stages. Okay, first stage is known as staging. Okay, first stage is known as staging. You send the transaction to a staging area. Okay, where it stays for some time. Okay, and then from staging area you create a second transaction, and the staging area is also on chain. Okay, so you create a transaction, you send it to a staging area, and that transaction gets confirmed on the blockchain. Now, from the staging area, you again create another transaction and then send it to the recipient. While that transaction is in the staging area, if you notice any discrepancies, if you realize that maybe the address is wrong, or if you realize that your private key has been compromised, then you can revert back. You can return the funds from the staging area back to your address. Okay, so then this two-step transaction gives you time. If you made any mistakes, right, you can undo it. Unlike the conventional way of spending bitcoins, if Alice is spending one bitcoin directly to Bob, she makes any mistakes. Okay, instead of Bob's address, she copies somebody else's address. Then there's absolutely nothing she can do about it, right? The money is gone. But with vaults, what you can do is the payment goes in two stages, right? First, it goes to the staging area and it gets confirmed on the blockchain. Then from staging area, you create another transaction which goes to the actual recipient, right? So when the transaction is in the staging area, if you notice any discrepancies, any errors, or your private key has been compromised, or for some reason you don't want to go ahead with the transaction, you undo that transaction, okay, quote unquote undo. You revert it back to the address of origin. That's what a vault is, right? So it's generally and usually used in cases of like big payments where a mistake could probably cause you life-changing losses. That's what a vault is, right? How it fits into our description of covenants, it's pretty obvious, right? Because in covenants, what do? We lock the outputs, right? We lock the outputs. I just gave an example that if Alice sends the payment to Bob and Bob wants to send it to Charlie, Bob can create a template and lock the outputs of the UTXO to Charlie's address. So once Alice sends it to Bob and Bob gains ownership, then using Bob's private key, that UTXO can only be sent to Charlie, right? Because it's been locked in the template. So with vaults, what you can do, you can lock the output, right? You can lock the output of the transaction in the staging area to the eventual recipient, right? So if the first transaction happens, it goes from the sender to the staging area, and then staging area it is already locked. It is already locked with the address of the recipient, for example. So even if somebody compromises your private keys in the staging area, let's say, they will not be able to hack your funds because you've already locked the outputs of your transaction, which is in the staging area. to the address of the final recipient, right? So that's how all of this comes into picture. All of this, like, solves the jigsaw puzzle. What covenants are, what OpCTV is, and how they have a use case in vaults. Okay. Now, what happens with object template verify is, like I just now mentioned, that you create a template, right? Those template might have these fields, right? You can already decide that I will spend this transactions and how many inputs will I use, which inputs will I use, what will be the log time, what will be the value of each input, right? And the script of each output and the number of outputs and the transaction version to use. Okay. Now, the template commits to all of these things, right? And once you've committed to all of these things, you can't undo them, right? And object template verify in its current form, it commits also to the exact value of the output. Exact value of the output, meaning you can't change the value of the output. You cannot change the value of the output, right? So if you've created a template and you have committed to the value of the output, then once you have received the transactions to that address, you cannot change the output. Okay. Now that can have that makes it less flexible, right? Because what if the fee varies, right? We know the fee environment varies constantly. The fee environment varies constantly, and if you have locked the amount of outputs, if you have locked the amount of outputs, and if you don't have adequate fee, then there's nothing you can do about it, right? There's nothing you can do about it. You probably have to add a child to it, or something like that. You'll have to pay exogenous fee, basically, or pay to the miners out of bank, because you have committed to the amount of the output, and now the fee, let's say, has increased. Once the fee has increased, you don't have adequate balance, you don't have adequate money to pay for the fee, right? Because if let's say your input is 1 Bitcoin, your output is 0.99 Bitcoin, okay, and the rest you've left for the fee. What if the fee is higher, right? What if you'll have to pay let's say 0.02 Bitcoin? In that situation, your transaction will not go through because you have locked and committed to the value of the output. Now you cannot adjust the fee endogenously. You probably have to attach a child to it, or you'll have to pay to the miner out of band, right? So this proposal makes it more flexible, such that using OpCTV, you will not have to beforehand commit to the actual value of the outputs, the exact value of the outputs. How does that happen? You use these two opcodes. One is op template hash, and the other is op input amounts. Okay, we'll see. We'll just read through this and try and wind this up in like 5 or 7 minutes. We've taken a lot of time on this one. Where is the article? Just see in brief how this works. Uh, Let's read this, okay? So two additional opcodes to consider as an addition to object template verify. Op template hash and op input amounts. Together, they relax the strict limitations that object template verify imposes, because it explicitly commits to the output amounts and therefore implicitly commits to the spendable input amounts in a lot of cases, right? As we discussed that the contemporary proposal of OpCTV explicitly commits to the output amounts. Meaning, once you've created the templates, there's no way you can change the value of the outputs, right? Now, how do we bypass this restriction and relax it using what this proposal is? It's known as CTV++. The author has named it as CTV++. Two additional opcodes to consider as an addition to object template verify, op template hash and op input amounts. Together, they relax the strict limitations that object template verify imposes, because it explicitly commits to the output amounts and therefore implicitly commits to the spendable input amounts in a lot of cases. So we will not go into the script, okay? Op input amounts, taproot only. So basically, these two opcodes firstly are compatible only with taproot transactions. Consumes a 32-bit signed integer n as parameter, okay? So you need to specify basically a parameter which will be denoted by variable n. This parameter can have three values, okay? First case n is 0, return the sum of all input amounts with the same script. Return the sum of all input amounts with the same script, okay? So instead of specifying the specific value of the output, right? Instead of committing to the exact value of the output, what are you committing to? We are saying that all the inputs in that transaction that have the same script, okay, club all of them. club all of them and use their clubbed value as the output, right? So let's say I have a transaction which has three inputs: 0.5 BTC, 0.6 BTC, 0.3 BTC, right? That's 5 plus 6, 11. That's 11 plus 3, 14, right? That's 1.4. Okay. So dynamically, it will sum the values of the inputs of all the UTX source, and then it will figure out dynamically what the input is, right? So you are beforehand not saying that, hey, I'm committing to 1.4 Bitcoin. No, you are saying that I am committing to the sum of the inputs of all the transactions that have the same script. So the script will dynamically calculate, as you can see, there's a for loop. It will dynamically calculate all the input amounts that have the same script, and it will keep on summing them, right? In our example, 0.5 plus 0.6 plus 0.3, that's 1.4 Bitcoin, right? Out of that, it'll deduct the fee dynamically. Out of that, it'll deduct the fee dynamically, and then whatever is remaining, it'll pay. Whatever is remaining, it'll pay. Okay. So in the contemporary OpCTV, what were we doing? We were specifying beforehand that, hey, Alice wants to pay 1.4 Bitcoin to Bob. Okay. Once you have committed that Alice wants to pay 1.4 Bitcoin to Bob, there's no going back. There's no way you can undo it. Alice will have to pay 1.4 Bitcoin to Bob. Now, what are we doing? We are saying that Alice will pay the Alice will pay X bitcoins to Bob. Alice will pay X bitcoins to Bob. And that value X will be dynamically calculated. How will that value X be calculated? If I specify n equal to 0, then in that transaction, all the inputs that have the same script, their sum will be calculated, right? 0.6 plus 0.5 plus 0.3 in our example. Now that's 1.4. Okay. And then what if the fee increases? Then we take the fee from it, right? So in earlier situation, if I had allotted 1.4 Bitcoin to the recipient and zero point 0.1 Bitcoin for fee. Let's assume a hypothetical number. Okay. If the fee is more than zero point 0.1 Bitcoin, my transaction will not get confirmed. I'll probably have to attach a child to it, or I'll probably have to do some out of band payment, right? Now I'm not committing to the exact value of the output. I'm just saying that take all the inputs, take the value of all the inputs that have the same script. Okay. And then from that, deduct the fee dynamically. So if it's 1.4 Bitcoin and the fee is 0.2 Bitcoin, then take that 0.2 Bitcoin and pay 1.2 Bitcoin to the recipient. That's what it's doing, right? So initially we were statically specifying and committing to the exact value of the output that the template will include, right? That we will commit to. Now we're not doing that. We are committing to the sum of all the inputs which have a common condition on them, it could be the sum of all inputs with the same script. It could be the sum of the last n inputs. It could be the sum of the first n inputs, right? So we are clubbing the number of inputs based on a certain condition and dynamically calculating the output, and then endogenously paying the fee, and then adjusting the output dynamically. And once that output is being adjusted dynamically, then that dynamically adjusted output will be given to object template verify. Then that will be given to object template verify. We're not doing away with object template verify, right? We have opt template hash, okay, which will have the other conditions, maybe the time lock, etc., etc. And then we have op input, which will dynamically calculate the value of output so that we don't have to commit to a specific value of the output. Once we have used these two opcodes, then we will know dynamically what is the exact amount of output we want to pay to the recipient, and then that dynamically calculated output on the script will be passed over to op check template verify. Okay, so that is what this proposal is all about, right? That's what covenants are. That's what vaults are. That's how both of them come into picture. And opctv is one of the opcodes, one of the popular opcodes that is being proposed to activate the covenants of fork if it all it happens. One thing that was noted by developers is that it is very rigid. It's not flexible because you have to commit to the exact value of the outputs. And this is a proposal that tries to circumvent that proposal. I mean that rigidity, and allows you to dynamically calculate the value of the output on the stack instead of predetermining it. Right. So if there are any questions pertaining covenants, opctv, or op template hash, op input amounts, or vaults, please feel free to unmute yourself and ask. And I will just have a look at the chat section if there's something else we can move on. Thanks for listening. The age may BTC lena legal है क्या? That is not a question for me, I guess.
That's
So I'll move
something
on.
for older session. Acha,
Yeah.
Fazal, I had a question on
Yeah.
So broadly, I could understand parts of it, especially, but like still the new opcodes that are being proposed. Earlier, I remember you used to share like notes on it. Is it possible like we can probably after the session or sometime we can figure out how can you, because when you're explaining stuff, it
Hmm.
becomes a little difficult for me to concentrate because the screen is on CTV and then you're explaining a lot of stuff. Sometimes a little beyond. So is it possible to maybe write on the screen or something like that so that I can maybe focus a little more on the content being spoken?
I don't know how is it possible to write on the screen. I mean, I believe I'm not really sure. I believe either you need a device which is compatible with a stylus, or maybe people use the mouse to draw. I've never done that. Like how is it done?
Okay, we can do some research on it because that will sort of be good to just keep the attention. Sometimes probably it's just me, but I just wanted to,
Right, right.
yeah. But I could follow along most of the stuff except for the new opcodes that are being proposed. But I'll go through that maybe later.
Right. So there was a short tenure of time where I used to actually write notes, but currently my schedule will not permit me to do that. But yeah, on the go while we are in the session, we can jot down stuff.
Yeah, yeah.
So yeah, maybe we can yeah.
I'll also do a research, and if others have any feedback as to what tools people use to conduct live classrooms, to
Mhm.
so that instructors can jot down on the screen itself, that might be nice addition.
Yeah, yeah, cool, sure. Okay, all right. Let's move on to the next one. This one is about mining. Adjusting difficulty beyond 256 bits, and is posted to the Bitcoin Dev mailing list with a concern about adjusting proof of work difficulty beyond the 256 bits available in a block header. That would require an unfathomable increase in hash rate, an increase of about 2 to the power 176 times the current rate. But if it were to happen, Michael Castano notes that a fork could add a secondary hash target, and both the primary target and the second target would need to be met in order for a block to be valid. This is similar to a proposal to mitigate block withholding attacks. These types of forks, which include proposals like forward blocks, may technically be soft forks because they only tighten existing rules. But some developers prefer not to use that label because they make it easy for non-upgraded full nodes and potentially all lightweight SPV clients to be tricked into thinking that a transaction has hundreds or thousands of confirmations when it actually has zero confirmations or conflicts with an actually confirmed transaction. Okay, so we all know more or less the anatomy of what a Bitcoin block header looks like, right? Every single person that I can see in this room, I'm sure has gone through mastering Bitcoin, and we all know what a block broadly looks like, right? It's basically classified into two sections. One is the header, and the other is the body, right? And we all know broadly what mining is, right? When we mine, we hash. We hash. Okay, would somebody like to take a shot because it's pretty quiet today, and this is a very straightforward question, I believe. What do we hash? Right? What do we hash to get the nonce?
What do we hash to get the nodes?
I mean, as a miner, you're hashing, right? There's a data, and you're
Yeah.
hashing that data. What's the data that you hash?
A block header.
Right. Okay. Because when I was new to Bitcoin, not even very new, even for a few months, you can say, like maybe even 4 to 6 months, I used to think that the entire block is hashed, including the transactions. But then I figured out that no, it's you don't hash the entire block. You only hash the header, right?
Yeah.
So yeah,
I
correct answer, Ashkan. Yeah,
yeah, thank you. I only
I
know
yeah,
it
yeah.
also
we also
recently.
Sure.
posted it.
Others should also share how like dumb they were in the first 6 to 8 months. So please feel free to go ahead and say. You were saying something, Steve. I was not able to hear it.
Yeah, I was saying Coding P already posted it in the chat.
What gets hashed? Just let me see.
She posted what gets hashed the moment you asked
Do I
the
You
get
hash
any
the header.
advantage
She's
for
smart. No, she's not like us. She's
do I
not
get
like
any
us. She's
advantage
smart.
for unmuting myself?
She's a quick learner. We were dumb. I used to think he hashed the entire header. Then one day I read it somewhere and I was like, this has to be a typo. You don't hash the header, you hash the entire block. Then I read it at multiple places that you only hash the header, you don't hash the entire block. So yeah, I'm sure there's somebody over here who believes that we hash the entire block, but they're not coming out of embarrassment. But no worries, yeah, we hash the header. Cool. All right. So we hash the header, okay, and uh, by difficulty, basically we are constantly looking for a number, right? We are looking for a nonce. That nonce needs to have a certain number of zeros. Okay, a certain number of zeros. So the nonce value is up currently up to 256 bits. Okay, which is I think currently we are only occupying 30 to 40 bits. I think so. If the nonce is 256 bits, the difficulty currently I'm guessing it's around 30 to 40 bits. So there's still a lot of time for us to exhaust all those 256 bits, such that all 256 bits have to be 0, 0, 0, 0, 0, 0, 0 all the way to the last one, right? But we keep hearing about this in social media every day. Countries are planning strategic Bitcoin reserves, and countries are investing in ramping up their infrastructure. And I keep hearing about how Oman is building a Bitcoin mining infrastructure and investing $2 billion in it. And we keep on hearing about how secretly Russia is buying it, and UAE is buying it, and Bhutan is buying it, and they are trying to set up a strategic Bitcoin reserve, and how USA is planning to buy a strategic Bitcoin reserve. We don't know how much of it is substance and how much of it is only noise, but we keep hearing that nation states will start mining, etc., etc. And with if that happens, then we can expect an exponential increase in the hash rate. Okay, so this is a proposal by Anders, who is far-sighted, basically. He has, I mean, because that field is 256 bits, right? What if the difficulty increases so much that all those 256 bits get exhausted, right? Currently we're probably using 30 bits or 40 bits. Okay, what if, I mean, the hash rate will have to increase this much. Okay, it'll have to increase this much. So if it increases this much of the current hash rate, then all those 256 bits will have to go to zero. But then how do you increase the difficulty further? Because if all 256 bits are exhausted and you want to increase the difficulty further, you can't do that, right? Because that nonce field is only 256 bits. So what do you do after that? After that, this proposal uh, says that, okay, let's read what the proposal is. Firstly, I even doubt this would happen sometime soon. Has he given some time frame? No, I don't think so. I doubt this will happen sometime soon. Yeah, but some people have a tendency of thinking about what happens in 2106 or something like that. So let's just read the proposal. I've been looking into the long-term implications of the Bitcoin hash rate growth for the difficulty adjustment mechanism, and I'd like to discuss a potential concern related to double exponential growth. As we know, the difficulty adjustment mechanism aims to maintain an average block time of approximately 10 minutes by adjusting the target value every 2016 blocks, right? So every 2016 blocks, we adjust the difficulty, okay? And this difficulty adjustment is nothing except the fact that we decide how many zeros do we need in a nonce, right? Whether you need more zeros than the previous difficulty adjustment period or you need less zeros. This target value, when represented in hexadecimal, effectively determines the number of leading zeros required for a valid block hash. The Bitcoin hash rate has historically shown a strong exponential growth trend driven by advancements in ASIC technology. However, some observations suggest that this growth might be accelerating, potentially exhibiting double exponential growth, meaning the rate of exponential growth is itself increasing exponentially. If the hash rate were to continue to grow at a double exponential rate, the difficulty would need to increase at an accelerating pace to maintain the 10-minute block time. This would mean the number of leading zeros in the target value would also need to increase at an accelerated rate. Since the target value is a 256-bit number, 64 hexadecimal digits, there is a finite limit to the number of leading zeros. Sorry, number of leading zeros. Where did we go? Number of leading zeros observed. Okay, I'll read again. If the hash rate were to continue to grow at a double exponential rate, the difficulty would need to increase at an accelerating pace to maintain the 10-minute block time. This would mean the number of leading zeros in the target value would also need to increase at an accelerating rate. Since the target value is 256-bit number, that's 64 hexadecimal digits. There's a finite limit to the number of leading zeros it can have, with the approximately 90-20 leading zeros currently. So currently we're using 90 to 20 leading zeros. There are only about 45 to 50 left zeros. Okay, so the maximum difficulty that we can have without a soft fork, we have currently utilized, let's say, one third of that. My concern is that with double exponential hash rate growth, we could reach this limit much faster than a simple linear projection would suggest, potentially within a decade. Once this limit is reached, the current difficulty adjustment mechanism would become ineffective, potentially leading to unstable block times and network instability. My questions: has there been more formal analysis of the Bitcoin hash rate trend to assess the likelihood of double exponential growth? Are there any existing studies or analysis I should be aware of? The second question, if double exponential growth continues, what are the most promising approaches to address this potential issue in the long term? The third point is, third question is, what are the trade-offs associated with different solutions, such as more frequent difficulty adjustments, changing the difficulty adjustment algorithm, or changing the proof of work algorithm? So basically, the doubt or the question that this person has handles is that currently we are using one third of the available space for the nonces, right? We can have 45 to 50, whatever that number is, 45 to 40. We can have 44 to 45 leading zeros. After that, we will exhaust the 256-bit space that we have for the nonce. We're currently using 90 to 20 leading zeros, right? What if there is a double exponential growth in the hash rate over the coming years, next 10 years, 15 years, something like that, and we exhaust all the available zeros? What do we do after that, right? So there is an answer given by Michael Fasano, and he says a solution is to keep miners on SHA-256 instead of switching to a hash that allows for a larger range of difficulty targets, but to require them to hash again to achieve a secondary difficulty header. At max target difficulty, miners would publish blocks with SHA-256 header equals to 1, and when SHA-256 off SHA-256 header, which is the secondary target, where the secondary target is just up and down if primary target is 1, where primary target represents today's target difficulty. Nodes then verify blocks by checking SHA-256 header is 1 and SHA-256 header is less than the secondary target. Okay, so when my understanding of this proposal is that, because the answer is very succinct. So my understanding is that we will have two nonces. We will have two nonces. Okay, the first nonce should completely get exhausted. So the first nonce should have complete zeros. Okay, then we take that nonce and we use that nonce and pass and SHA-256 that nonce again. Okay, so this is our header. We hash it, right? This is our header. We hash it. This is our first nonce. So the first nonce should have 45 zeros. Okay, should have 45 zeros, meaning it should exhaust the 256-bit number. Then we take that nonce and hash it again. That is a secondary target, and then we adjust the secondary target up and down depending on the difficulty, right? So a miner will find a block only if the miner hashes the header, and the first and the hash of the header leads to all zeros, meaning all 256 bits are exhausted. Okay, and then after that it takes that same header and double hashes it, and after double hashing it, it'll have a secondary target, and then that secondary target will have zeros, like it might have uh, one leading zero, and then if it goes up two leading zeros, and then it goes up three leading zeros. So we'll do that. Okay, instead of changing the header, the the algorithm, right? Because SHA-256 algorithm, as the name suggests, it can only give you an output of 256 bits, right? So one proposal is to change SHA-256 to another algorithm, which gives you an outputs of greater than 256 bit numbers, right? So if you have a greater output than 256 numbers, then you will have more than 44, 45 leading zeros, right? But then I believe that would also lead you to change all the ASICs in the world, which are used for Bitcoin mining. They are specialized in SHA-256 mining. So you'll have to get rid of all the ASICs, and all the mining companies will have to upgrade their mining infrastructure, which is obviously very tedious and cumbersome and expensive. So one fix would be that uh, we'll have two difficulty targets. If the first one gets completely exhausted, we go to the second one. And only if the miner completely exhausts, meaning the first difficulty target is completely zero, then we go to the second one, and we keep on adjusting the second one. So if both difficulty targets are met, then the miner finds a valid block, unlike what happens contemporarily, where we just find where we have one difficulty target, right? We'll have two difficulty targets and two nonces that we'll have to find, and both of them satisfying the each difficulty level, and that is how we will be able to mitigate this issue when and if we exhaust all the 256-bit space for the non. So that is what the proposal is, and that is what the reply is. And I really admired the answer, because this is the question that, I mean, even hypothetically, but also comes to me, like what happens when the difficulty goes so high that you exhaust all the zeros? What do you do after that? Because changing the hash algorithm, I don't see as a feasible alternative, right? Because there is mining infrastructure worth hundreds and millions of US dollars all across the world, and asking the companies to probably upgrade their hardware, it's not going to happen. So this I find is as a very feasible and a very easy fix that would just need a soft fork, right? Any questions pertaining this, please feel free to shoot them my way. Else we will move on. Something in the comment section. Audio only greater than Bitcoin only. What was this, Shian? I didn't get this.
I answered the question first, but I don't know still who answered the question first, but I answered on audio.
Okay, okay, all right, cool. Oh, okay. You answered it on audio and she typed it. That's what you're saying. Okay, but who was first? Do you remember? He was first or you were first?
No idea, no idea.
Okay, no worries. Anyhow, you all are not getting anything. Cool. So what is that? Will there be somebody's posting? It's Sandeepan. Will there be an incentive for miners to upgrade to this soft fork hypothetically? Not an incentive. I mean, it'll be compulsory. You will have to upgrade. Otherwise, like how do you adjust the difficulty, right? You have to constantly adjust the difficulty to ensure that the the average time in which you find a block is 10 minutes, right? Because if it's quicker than 10 minutes, then the settlement time becomes too small and there are more chances of hard forks. And if the time is too longer than 10 minutes, then like people will stop using Bitcoin, because like nobody's going to wait 30 minutes, 1 hour for a transaction to get confirmed on the blockchain. So you need to adjust difficulty to ensure that a block is mined every 10 minutes, right? How do you do that? You do that by constantly increasing the number of zeros in the nonce that you have, right? Currently, let's say you can have 44 to 45 zeros maximum. We have 90 to 20, right? So as the hash rate keeps on increasing from 20, we go to 21, we go to 22, we go to 25, 30, 44, 45. What if in our lifetime we come at a stage where all 45 zeros get exhausted? Then you can't increase the difficulty anymore, right? And the hash rate keeps on increasing and the difficulty is not increased, then the average amount of time in which you find a block keeps on decreasing. It goes from 10 minutes to 9, 9 to 8, 8 to 7, maybe then 1 minute. And if you find a block every 1 minute, it's going to be chaos, because there are going to be hard forks everywhere. There are going to be block races everywhere. Multiple people are going to find blocks and multiple people are going to propagate those blocks. And the entire network will have just 60 seconds to come to consensus, right? And you know there's latency on the Bitcoin network, so you don't want that to happen. So what is an avenue of circumventing this? It is to have a secondary target. So this soft fork will not be optional. It will be compulsory. Otherwise, the average time in which a block gets mined will get reduced. Will keep on reducing till it goes to 1 minute and 30 seconds and 15 seconds and who knows what. And if that happens, then there are going to be frequent soft forks. Like every once in a while there are going to be soft forks, which you don't want to happen. So it'll be something that everybody will have to agree on until the system reaches consensus. Maybe uh, yeah, I mean, like I don't know, but like when will that happen, Shah? Maybe SHA block header end time should also be a parameter in difficulty. Currently, we just have the SHA of the block header, and then this proposal is SHA of the block header. I don't see this happening in our life. I don't even see this happening in our life. This is a proposal. I don't see it happening in our lifetime. I don't see the difficulty increasing to that level. But if it happens, then the mitigation suggested is good enough. We won't see SHA increase in our lifetime. I don't think so. Cool. I'll come back to the comments later if any. Oh, we can move on. Yogansh is typing something. We'll take one more, and it's 8:54. We'll take one more in 5 minutes. Let's see the smaller one. So let's take this one in sequence. quantum computer upgrade part. Matt Corello posted to the Bitcoin dev mailing list about adding a quantum resistant signature checking opcode in TypeScript to allow funds to be spent even if ECDSA and Schnorr signature operations were disabled due to forgery risk from fast quantum computers, right? So we know there's a lot of talk about quantum computers, and I think this is pretty unique to this section, this changing consensus section that is a new addition to the Optech newsletter. We talked about things that will happen in the future, like exponential increase in the hash rate, double exponential increase in the hash rate. Now we're talking about quantum computers. So this is probably in this section we'll most probably be talking about things that are far-fetched in the future, right? Yeah. Where did it go? Yeah. So Matt Corelli posted to the Bitcoin dev mailing list about adding a quantum resistant signature checking opcode in TypeScript. Okay. So currently we have different signature checking opcodes, right? Some are used for legacy scripts and segwit scripts, and some are specific to TypeScripts, right? So we have opchecksig and we have opchecksig verify. We have opchecksig and we have opchecksig verify. These are used for legacy scripts and these are also used for segwit scripts. And then we have opcheck multisig, opcheck multisig, which is specific to TypeScripts, right? Because we with Taproot we enabled signature aggregation. Like multiple people can come together and aggregate their signatures into one single signature. And if they spend that transaction on the Bitcoin blockchain, it will be non-distinguishable from a transaction that is signed by one single person, right? So three people come together, for example, they aggregate their signatures. The signature looks the same as if it was signed by one single person, right? So you can't distinguish on the blockchain. It kind of enhances your privacy. This is known as public key aggregation and signature aggregation, which are TypeScript enabled, and it has a special opcode that checks it, that validates it. It's known as opcheck multisig, right? So for legacy scripts and for segwit scripts, you have opchecksig and opchecksig verify, and for TypeScripts, we have opcheck multisig. Okay, but all of these basically use ECDSA signatures or Schnorr signatures, right? And ECDSA signatures and Schnorr signatures. What if their resistance is broken by quantum computers? What if their resistance is broken by quantum computers? What do we do that, right? So this proposal talks about this. Matt Carello posted to the Bitcoin Dev mailing list about adding a quantum resistant signature checking opcode, right? So we have opchecksig right now, we have opchecksig verify right now, we have opcheck multisig right now. None of them are quantum resistant. None of them are quantum resistant. So Matt Carello proposed that we need to come up with a soft fork which has a which upgrades to a quantum resistant opcode, signature checking opcode, right? Because if quantum computers are able to break ECDSA and Schnorr signatures, then we need a signature scheme that is resistant to, to quantum computing. And with that, we also need an opcode that can verify those signatures, right? Because we need a specific opcode, a special opcode that is designed to verify transactions that have been signed using a signature scheme that is immune to quantum computing. So he proposed that we should go ahead with the soft fork or start discussing with the soft fork that incorporates another opcode. We have opchecksig, we have opchecksig verify, we have opcheck multisig. We should add another opcode which can be used for validating digital signatures which are quantum resistant. Okay, which are quantum resistant in case quantum computers are able to break the ECDSA algorithm. Okay. Uh, let's see further. Luke Dasher noted that the soft fork is unnecessary at present as long as there's a widespread agreement now about how quantum resistance checkpoint future. I users need to commit to it as an option which may become available later. Okay. So again, this proposal is specific to TypeScript, right? This is specific to TypeScript. So what Luke Dasher says is that we need to figure out a quantum resistant digital signature scheme, B, an opcode that validates quantum resistant digital signatures, but we should not go for a soft fork right now, right? Because quantum computing is not an immediate threat to us, right? So we need to figure out that when this happens, how will we combat it, right? We need to be ready. We need to have our ammunitions in place, but there is no urgency for a soft fork. We need to just, as long as there is consensus that when the need arises, we are ready to upgrade, then we upgrade. There is no need to do a soft fork and incorporate these changes into Bitcoin's consensus rules right now. We just need to figure out the solution and keep the solution ready. When we believe that quantum computing is actually a threat and it's on our neck, that is when we trigger the upgrade. Okay. That Reader suggested a transitory soft fork that would temporarily restrict the use of quantum insecure ECDSA and Schnorr signatures if it looked like quantum computers were on the verge of being able to steal bitcoins. Then, if anyone fulfilled an on chain puzzle contract that is only solvable with a quantum computer or the discovery of a fundamental cryptographic vulnerability, the transitory soft fork would automatically become permanent. Otherwise, the transitory soft fork could be renewed or allowed to lapse. Okay, so that's Visa. So three developers, they're Matt Corello for suggesting that we need to figure out a, a quantum resistant digital signature scheme and also an opcode and incorporate that in TypeScripts. Okay. Second suggestion was by Luke, who agreed with this proposal but believes that we don't need the soft fork right now. We need to keep things in place. We need to keep things ready because quantum computing is a far-fetched threat when it is actually sitting on our neck, or when we feel actually that there is a tangible possibility of quantum computers breaking ECDS and Schnorr signatures. Then we pull the trigger, and then that is when we activate the soft fork. And the third proposal is by Taj Rija, who proposes a transitory soft fork. What's a transitory soft fork? It's basically a soft fork that comes with a time span, like an expiry date. Okay, so we say that we are activating a soft fork with a an expiry date of 2 years. So for 2 years, this soft fork will be activated. Okay. After that, if users want, it will continue. If users don't want, it will expire, and you go back to the original state. Okay. So let's say we activate the soft fork. If we feel that we are threatened by quantum computers, we activate the soft fork. Okay, and let's say we put an expiry date of 2 years. Okay, and we put a puzzle. If somebody solves that puzzle, then that soft fork becomes permanent, right? And that puzzle will only be solved by a quantum computer. Okay, so we activate a transitory soft fork, let's say for 2 years. I'm just giving an arbitrary number for 2 years. Okay, if we feel threatened by quantum computers, and within 2 years, if somebody is able to solve that on-chain puzzle, it means that quantum computing has broken ECDSA and Schnorr signatures, and in that situation, that transitory soft fork becomes permanent. And if in 2 years, nobody, it's an arbitrary number again, if in 2 years nobody is able to solve that puzzle, it means quantum computers are not robust enough to break ECDSA and Schnorr signatures, and then that soft fork expires and we go back to the initial state, knowing that quantum computing is not an imminent threat to us. So three different proposals by three different developers on how we tackle quantum computing. We are past 9. That's it from my end. I will stop sharing the screen. Need to drop off. Good night. Good night, Shreya.